Okay, so we're given this second order differential equation. We're asked to convert it into state space and then find the output vector for the system. The output is y here, which is the displacement of, well, it's, yeah, whatever this dependent variable y is. It could be displacement, it could be something else. Okay, so system here is second order. And that means we're going to need two state variables. To that end, we're going to say here, I'm going to use x1 is equal to y, x2 is equal to y dot. You can use y1, y2, it doesn't matter. We're going to take the derivative of those. We'll get x1 dot is equal to y dot, which is equal to x2. And then we'll take the derivative of the second equation. X dot 2 is equal to y double dot. So now we need to take our original equation and solve for y double dot. Get m y double dot plus b dot, b times y dot plus ky is equal to u. We can solve this for y double dot. We'll get y double dot equal to x2 dot equal to minus 1 over m times the quantity b times x2 plus k times x1 minus u. We place this then into state space form. And our state space form, we're going to get x1 dot is equal to x2 x2 dot is equal to minus 1 over m times the quantity b times x2 plus kx1 minus u. Those are the state space equations, not in matrix form. In matrix form, we're going to get, first we're going to just say, we're going to say that z dot is equal to the vector x1, x2. In fact, we're going to use x dot here. Sorry, we're going to say x is equal to the vector of x1 and x2, and then x dot is equal to the vector of x1 dot and x2 dot. You could use z if you want. For this, it doesn't matter. And then in matrix form, we're going to get here that x dot is equal to ax plus bu, and then a here is equal to matrix of 0, 1, minus 1 over k, and then minus 1 over b. And then our capital B matrix, this is just going to be 0 and then 1 over m. And then we can now look at our output. So the output for the system is y is equal to c x plus du, and this is in our vector form. And we also know that y must be equal to x1, because that's our displacement variable. So that's this displacement state variable. And we got that, that really just comes from right here. So our output is just the displacement y which is equal to the first state variable. So then from inspection, the matrix C must be 1, 0, and the matrix D must be equal to, well, it's just 0. Such that Y is equal to 1, 0, multiplied by the state vector of x1, x2.
For the A matrix, would it not be like K over M?
Oh, yeah, sorry. Yeah, that's wrong. Yeah, I was missing an M in the 1 over M in my B matrix in my notes, and that tripped me up here because I was thinking about that while I was writing this. So we should have minus K over M and minus B over M in the A matrix.
Could you explain again how you got your C and D matrices?
Mm-hmm. So you're told what the output is. In this case, the output is Y. Y is the displacement for this oscillator, let's say. When we went to define our state space variables, we said here that our first state variable is equal to Y, or equal to the displacement. And so from right here, we can really get the output equation from right there, is the fact that it needs to be equal to x1, that's our state variable, and there's no contribution from Y from x2, or from the second state variable. So in this case, we end up with, first of all, there's no U in our output. Now, if I said the output was Y plus U, then you would need to include that in there. You would need to find a D there. So in this case, the equation is the C matrix multiplied by the state vector, which is x1, x2, and then the direct transmission matrix D multiplied by the vector of whatever inputs are. And in this case, we said the inputs do not contribute, so that has to go to 0. And since the output is just a single state vector, we must end up with a 1 here and a 0 here. We take this row multiplied by that column, you get x1 plus 0 times x2. Yeah. So in this case, it's relatively simple. It may not always be so simple. You could, for example, choose to have the acceleration be your output, and then you would need to incorporate the equation of motion into your C matrix. And then you would also have a term contributing from the direct transmission matrix, or from the input. Any other equation or any other questions? All right, in that case, we're going to move on to the transfer matrix, where we're going to end up defining what a transfer matrix is for a state space problem. We'll do an example, and depending on how much time we have, we may look at state space modeling of systems with input derivatives. Okay, so we're going to consider a multiple input, multiple output system, or what's known as a MIMO system. We're going to assume that there are R inputs, so U1 up to UR. We're going to assume that there are M output systems from Y1 up to YM. We're going to define our input vector U as being, well, it's simply the vector U1, U2 up to UR, that transposed. And then we'll define our output vector Y as collection of all of our outputs, Y1, Y2, up to Ym. So then our transfer matrix, which we'll write as G of S, relates the output Y of S to our input vector U of S. So we would assume somewhere that you've done a Laplace transform and you've converted into the complex domain, so everything is now dependent on S rather than on time. And then we can write here that our output is equal to this transfer matrix G of S times the input vector U of S, or sorry, the Laplace transform of that input vector. And then here, this G of S, I'm not going to derive it, I'm just going to give it to you, is going to be equal to the C matrix times S times the identity matrix minus our system state matrix A, that inverse multiplied by the input matrix B plus the direct transmission matrix D. Okay, we're going to consider an example where we go and find this transfer function. We'll end up with, well, we have two state variables here, or we have two state variables, two outputs. We also have two inputs. Because we have two outputs and two inputs, we're going to end up with our transfer matrix being a 2 by 2. So there will be a transfer function for each output corresponding to each input. So 4 of them in total. We're given the following system shown here. And then we're going to go ahead and we're going to write this out in matrix form. So we'll just say the system can be written in matrix form. As we're just going to write this in the generic form, we'll have x dot is equal to ax plus bu. Y is equal to cx plus du. That's just our general form. And then I'm going to say here that the transfer function matrix G of S relates Y of S to U of S. This means that we can write Y of S is equal to G of S times U of S. And our goal is then going to be to find this G of S. We're going to take the Laplace transform of both of these equations. So we're going to say to find G of S, we Laplace transform the state and output equations. So we get the Laplace transform of x dot is equal to the Laplace transform of ax plus bu. And we are going to apply this directly to the matrix equations rather than each individual equation. This is going to give us here s times x of s minus x0. And these are vectors still. This is then equal to a times big X of s plus b times big U of S. For the output equation, we'll take the Laplace transform of y is equal to Laplace transform of cx plus du. This is going to give us big Y of S equal to C times big X of S plus D times big U of S. Okay, we're going to assume 0 initial conditions. So we're going to assume x of 0 is equal to 0. That's just standard for transfer function analysis, such that we're going to get S times big X of S is equal to A times big X of S plus B U of S From here, we're going to bring everything with a big X of S in it onto the left-hand side. So we're going to get S to big X of S minus A big X of S. That's going to be equal to BU of S. From here, we can pull out a big X of S, but we'll need to keep an identity matrix inside here. So we'll get S times our identity matrix minus A. All of that multiplied by big X of S is equal to B times U of S.
Did anyone return a MacBook to this room?
Not to me.
Okay, it was like an earlier class. Do you know if there's like a place that because it shows that it's in this building? So I'm not sure if there's like a lost and found.
There is generally, I don't know
No, okay.
if there is a lost and found in here.
No worries.
Yeah, there should be some. If you go through, if you go out the door and go across the hall into the other building, there should be a staff office around that account. Yeah. Okay. So from here we can solve for big X of S. We can find big X of S is equal to the inverse of the quantity S times I minus A. That inverse times B U of S. Hopefully that inverse exists. If it doesn't exist, you're in trouble. From here, we can take this. We now know what X of S is. We can plug that up into our output equation. And then we'll end up with that big Y of S is equal to quantity C, that's our output, times SI minus A, that inverse applied to B, plus D, all of that multiplied by U of S, such that just what I just wrote here, G of S is equal to C times SI minus A inverse B plus D. So I guess we did end up deriving it. For this system, our direct transmission matrix is just zeros. So we can just eliminate D here, such that G of S is simply what's shown up there. For our C matrix, I'm going to rewrite those here so we have them. C is the identity matrix, 0, 1, 0, 0, 1. Our A matrix is -1, -1, 6.5, 0. And then the B matrix is 1, 1, 1, 0. We're just going to go ahead and start plugging these in here. So G of S is equal to 1, 0, 0, 1 times the matrix X 0, 0, S, that is S times the identity matrix, minus A, which is -1, -1, -1, 6.5, and 0. We'll need to take an inverse of that. And then that's then multiplied by B, which is 1, 1, 1, 0. Inside the parentheses, we're going to end up with the matrix S plus 1, 1, minus 6.5, and then S. And that needs to be inversed. It's not a simple inverse because it's not a diagonal matrix. And then also we have here 1, 1, 1, 0. And so from here, if you go and carry this out, you will find that G of S is equal to, first we'll get a fraction 1 divided by S squared plus S plus 6.5. And that multiplies a matrix of S minus 1 times S, and then S plus 7.5. And then lastly, 6.5. Okay, so then, thus we will get y1 of s, y2 of s. These are equal to big matrix with a fraction in each entry. In the first one, we're going to get fraction s minus 1 divided by s squared plus s plus 6.5. The next one, we're going to get s divided by s squared plus s plus 6.5. And s plus 7.5 divided by s squared plus s plus 6.5. And then lastly, 6.5 divided by s squared plus s plus 6.5.
Doesn't that have to multiply by u of s?
Oh yeah, I'm not there. I'm not done yet.
Okay.
But yeah. And then lastly, we'll get u1 of s and then u2 of s. So then the four transfer functions are, we're going to get y1 of s divided by u1 of s is going to be equal to s minus 1 divided by s squared plus s plus 6.5. And then y1 of s over u2 of s is equal to s divided by s squared plus s plus 6.5. y2 of s divided by u1 of s is then equal to s plus 7.5 s squared plus s plus 6.5. And then lastly, y2 of s divided by u2 of s is equal to 6.5 divided by s squared plus s plus 6.5. That is the transfer function or the transfer function matrix for this particular system. Okay, we're going to take a look now at state space modeling of systems with input derivatives. And so these are systems whose governing equations involve one or more input derivatives. In this case, the variables that specify initial conditions are not going to be state variables. So things like the displacement and the velocity alone will not be state variables necessarily. So to illustrate this, we're going to consider the following example here. In this case, our equation of motion is going to be, and so we have, first of all, we have a mass connected with a spring to ground, and then a damper connects to it, and the damper is being excited by some input u of t. So in this case, our equation of motion is my double dot plus by dot plus ky, and that's then equal to b times u dot. Or we can solve for y double dot, and this becomes minus k over m y minus b over m y dot, and then plus b over m times u dot. So let's choose state variables x1 equal to y, and then x2 equal to y dot. Then we're going to get that x1 dot is equal to x2. x2 dot is then equal to minus k over m x1 minus b over m x2 plus b over m u dot. Okay, so this form is only valid for certain inputs. So for example, if u of t, which is just a general input right now, if that is the unit impulse, then the integral of equation 15 is going to give us that x2 is equal to minus k over m times the integral, we'll just say y here, dt, minus b over my plus b over m times delta t. And then since we have this Dirac delta appearing, it means that x2 at 0 is going to be infinity, and that is not acceptable for a state variable. We cannot have a state variable that has an infinite amplitude or an infinite value at any point in time. Now, if u is like a constant or some sinusoidal input, then this is okay. This state variable chosen are fine. For certain types, it's not okay, which means that in general, it's not okay. Okay, so we need to then choose some type of state variable such that our state equation will not include a derivative of u. And one way to do that is to define that x1 is equal to y, so that will be the same as before. Then x2 is then going to be equal to y dot minus b over m times u. And then we'll get, when we take the time derivative of that second equation, of equation 18, we'll get x2 dot is equal to y double dot minus b over m u dot. Then we can substitute in for y double dot. We get x2 dot is equal to minus k over m y minus b over m y dot plus b over m times u dot minus b over m u dot, such that we end up eliminating this u dot term. From that first state equation up there, or first state variable, we can solve for y dot. And that's going to be x2 plus b over mu. We now substitute that back into equation 20 here. And we'll get then that x2 dot is equal to minus k over m y. Oh, that should actually be an x1 minus b over m times quantity x2 plus b over m u, such that x2 dot is equal to minus k over m x1 minus b over m x2 plus b squared over m squared u.
Should that be minus b squared over m squared?
Yeah. Yes, it should. Yeah. Okay, our state equation then is, we'll have our vector of state variables x1, x2, and these are dotted. It's equal to the vector of 0, 1, minus k over m minus b over m. That gets multiplied by the state vector, so x1, x2, plus the input matrix is going to be b divided by m, and then minus b squared divided by m squared, and that multiplies u, and that is our state equation. All right, if the equation involves higher derivatives and multiple derivatives as well, then it becomes more complicated than what we just showed here. There are some systematic techniques that are covered by the Ogata book. We're not going to cover them here in this class. Okay, we're going to stop here